Good morning, and today's lecture is going to be on the continuous time Fourier Transform, also known as the CTFT. Now, in particular, what happens here is that in doing frequency domain analysis, it tends to be a lot easier to see certain characteristics of the signal instead of it being in the time domain. And what happens here is that when we do the frequency response for any time domain signal, we're going to see that there's only tends to have a constant gain up to a certain cutoff frequency, and then after that the gain just drops either linearly or non-linearly accordingly to the characteristic of the signal and the system it's going to be introduced to. For any signal frequencies that are more than the cutoff frequency denoted as FC, they tend to be attenuated and distorted because of this runoff that you see here for the frequency response. And the graph here that you see with the arbitrary, basically we're seeing where two people speak, and the solid line here that you're observing is basically for a male speaker, whereas the dotted line here you're observing is for a female speaker. And this is basically because what happens here is that male people tend to have lower frequencies than female people, so you tend to see this frequency being represented accordingly. Now, you actually have seen some of this frequency domain analysis being applied in like everyday signals, and the most common one you might tend to see is like if you have an equalizer for any sort of stereo, where you could adjust like the low frequencies being the bass, the high frequencies being the treble, and the mid frequencies being like the voice and so forth. For anyone who has done power system analysis, frequency domain analysis is quite essential for when you're analyzing harmonics, because harmonics can damage any equipment because they are waveform distortions that are superimposed onto the fundamental frequency waveform. In doing so, what happens, it causes distortion of the original waveform, and it can be quite detrimental to any machinery operation if this is not mitigated or controlled. So in short, the cleaner the signal is, the better you get for quality. Stock market fluctuation analysis also relies on frequency domain analysis, so to make predictions if the stock will rise or if it will fall. Audio and image processing uses a lot of frequency analysis as well in order to determine how they can clean signals, how they can filter it, and so forth. So, any frequency content for any signal is referred to as the spectrum of the signal, and the analysis of it is called spectrum analysis. In particular, when you need to analyze the spectrum of a signal, you actually do something. You need a piece of hardware known as a spectrum analyzer in order to do this. For software signals, it's actually a lot easier because the signal is represented in software, so you can do the spectrum analysis in software as well. And in particular, you can actually do this using MATLAB or some other sort of software that does this analysis for you. Now, recapping a little bit with regards to the Fourier series, if we had a periodic signal, this actually could be expressed as an infinite sum of orthogonal functions. But these orthogonal functions are basically cosines and sines, and the summation of these is what results into what we know as the Fourier series. So as of such, the frequency of each of these sinusoid functions is an integer multiple of the fundamental frequency when doing this. The guy who invented this is known as Jean-Baptiste Joseph Fourier, and he is credited for the discovery of the Fourier series with respect to mathematics, and then further on its application towards in any signal processing field. So let's say we actually had a square wave here being our original signal. We can see here that basically it's periodic. It's going to have a high and a low here, and it keeps on repeating at a certain time interval. If we Fourier series this accordingly, we basically get a series of sine and cosine here that actually keep on representing it. But because we only do like the first four terms, you actually don't see the representation of the square wave. But when we start summing the four terms accordingly, and we compare it to like the original signal, then we actually see that, okay, this is what actually happens, and during the summation point that we get close enough to an accurate representation of the signal. Now the Fourier series basically has a lot of different forms, like the raw form, the complex exponential form, the synthesis equation, the analysis equation, and so forth. But for the purpose of this lecture, we're going to be using the complex exponential form, which is going to be seen here in the following equations in the blue block and the yellow block. It is also important at this point to remember or recall the Euler relationships for expressing the Euler expression here known as E in terms of sine and cosine. This Euler expression can be found in your ECNG 2011 notes. If you can't find it, it's easily searchable online in order to get the actual equation for what e to the minus j theta is. It typically is going to be cosine of theta minus j sine theta. So in using this complex exponential form of the Fourier series, we tend to get complex Fourier coefficients noted as C of k given by the equation here, which is an integral equation, and k represents each of the harmonics. So at k equals 0, this is going to be the fundamental frequency, but at 1, 2, and 3, this is going to be the first harmonic, the second harmonic, and the third harmonic. In particular, if we took the magnitude of Ck, what this results is in the amplitude spectrum of the original signal being x of t. If we took the phase of Ck, however, we get the phase spectrum of x of t. So remember, this Ck here is going to be a complex number, so it is possible to get an amplitude being the magnitude of the signal and a phase being the angle of the signal. Also, the index k assumes integers values, so it cannot take any decimal values. It must always be integers. So that's why the amplitude and phase spectra appear at discrete frequencies noted as k omega naught, where omega naught is the original frequency of the signal. So if we go back to our classic example of the periodic square wave function, and we actually did the Fourier series for this, we basically will end up with the following equation here in the blue block. There's also a shorthand version to write this, which is known as sinc of whatever is in the brackets here. But for illustrative purposes and explanation, we're going to be using this raw form here in terms of sine. If we actually do the magnitude spectrum using the Ck equation, and we discretize it, we'll end up with the following graph here known as the sinc spectrum. And what we can observe here is that for the line spacing is going to be pi a divided by t, and the zero crossing points are going to be k equal to mt on a, where m goes from negative infinity to positive infinity, and m also only uses integer values. Now, note that as t increases, these lines that you observe here for the sinc spectrum are going to get closer together. Also, as a decreases, the mt divided by a factor being k is going to increase. What this means visually is that the zero crossing points are going to move apart and the curve itself is going to flatten. So as t increases, the pulse train spacing increases, and if we evaluate the limit here for this effect, we'll end up getting a single pulse. The spectrum of this single pulse, which we have, is given by the magnitude of c of k, and this results in a continuous sinc curve. As of such, these lines that you observe here, they merge together. So the takeaway point here is that the spectrum of a single pulse in the time domain is therefore a continuous sinc in the frequency domain. So I'm repeating that again. If the single pulse exists in the time domain and we perform the spectrum of this single pulse, the representation of it in the frequency domain is going to be a continuous sinc. Now, as a here in the following equations decrease, however, the zero crossings that we observe are going to move apart. But as A increases, the single pulse, as we just now observed before from the previous explanation, it will approach into a single pulse known as an impulse. So therefore, the spectrum of an impulse is an infinitely wide sink, which is in fact a flat spectrum. It's going to be one horizontal line throughout the entire graph in the frequency domain. And this brings us to one of the most important points regarding impulses. An impulse in the time domain, when you observe its spectrum, it shows this flat line across all frequencies, meaning that an impulse contains all frequencies at a constant magnitude. So any periodic signal is always going to have a discrete spectrum. And basically you could think of this like if we had a sinusoid graph. So if we had a standard sine graph or a cosine graph, it tends to have a set frequency. So if we try to get the spectrum of this, we already know what the frequency is. So it's easy to represent in this frequency domain. So the question here is what happens if the period increases. So as the period increases, we know that the line space in here is pi a divided by t. And the zero crossing points are given by this k factor here being mt divided by a, where m goes from negative infinity to positive infinity and m only takes integer values. So as t increases, the line space decreases. And as such, the spectral lines get closer together. The zero crossing points will move further apart, and as such, the spectrum flattens. So when you say that the spectral lines get closer together, what this means is that because the line spaces decrease, the spectral lines getting closer together means that the entire graph here approaches an impulse. Now the Fourier series applies to periodic signals, and it's quite representative for any periodic signal to break it down into a series of sum of series of sine and cosine functions. But for non-periodic signals, it doesn't tend to work very well. And this is because for a non-periodic waveform, there isn't really a set period. So a period for a periodic signal, meaning a non-periodic waveform, is that we tend to treat this as if it has an infinite period. And once we assume this limit as t tends towards infinity, we can then move towards formulating a new equation for solving for non-periodic waveforms. So as t tends towards infinity, that means the fundamental frequency is going to tend towards 0, because t is equal to 1 divided by f. So as the fundamental frequency approaches 0, all these limits here are being affected. This means that t here tends towards infinity. Omega naught, because omega naught is a function of the fundamental frequency, will tend towards 0, meaning that any change or any small change being represented as delta omega will also tend towards 0. K omega naught here will tend towards a general omega. Our ck factor will tend towards c omega. Or the fundamental frequency here will tend towards delta omega, where delta omega is a very small change in frequency divided by 2 pi. So as of such, if we apply all these limits into our general ck form here, being the complex exponential form of the Fourier series, what happens is that this evolves into our c omega form here. Now, one thing to note is that in the c omega form here, there's no k factor. The harmonic resonator does not exist in the c omega form. And this is because k omega tending towards omega. So now we have an infinite number of k values and we have a continuous omega. So c omega here is here, therefore a continuous variable. So the transformation of ck to c omega shows us how we can move from the time domain to the frequency domain and back. But however, remember here that t, we treated this as infinite. So therefore, in the equation, we just put the lower limit here for the integral being infinity. So observing this, what happens is that a periodic signal has a discrete spectrum, as we saw from all the previous slides and all the previous discussions. But for a non-periodic signal, the spectrum is going to be continuous. Now we can simplify the equation doing some normalization and substitution and so forth. And c omega here can transform into an x omega form here. And this form that we observe, being either the c omega form or the x omega form, is what we refer to as the continuous time Fourier transform for any x of t signal. So this is how we move a signal from the time domain to the frequency domain and gets its frequency domain representation known as the spectrum. Of course, because we move from the time domain to the frequency domain, there must exist an inverse Fourier transform to move from the frequency domain back into the time domain, and the following equation shows how this can be done. So basically, recapping, the Fourier transform allows you to compute the frequency domain representation of a signal from the time domain signal. So we are able to transform a time domain signal into the frequency domain. The inverse Fourier transform will do the reverse. It will transform a frequency domain signal back into the time domain representation. The CTFT and the inverse CTFT are known as the Fourier transform pair for regarding continuous time signals, and they only apply to non-periodic signals. So the Fourier series is used for periodic signals, but the Fourier transform is used for non-periodic signals. There is also a possibility how we can use the Fourier transform to apply to periodic signals, but we'll cover this later on in a lecture when we start discussing different types of Fourier transforms itself. One thing to note is that the continuous time Fourier transform is quite similar in form to the Laplace transform, and many of its properties are really similar. But there are some important exceptions that we will discuss later on, which I'm going to apply throughout the entire course. So this brings us to the end of this lecture, showing that how we are able to get the continuous time Fourier transform to transform a time domain signal to a frequency domain signal, i.e. getting its frequency domain representation, being its spectrum, and how we can use the inverse continuous time Fourier transform to move from the frequency domain to get the time domain representation of that signal. The next lectures that we're going to be doing will show how the continuous time Fourier transforms moves into the discrete time Fourier transform and then the discrete Fourier transform.